Hello everybody and welcome to the last but one session number 24 of my lecture on statistical energy analysis and hybrid methods. Today it's time for a hybrid FEM SEA example, and by using this example you will much better learn all these specific steps of hybrid simulation and it will hopefully become much clearer in this example case. Good. So the most interesting and clearest case of a hybrid example is a twin chamber. Why is that? Because both chambers are designed to be random by nature. I mean, this is the definition in the norm. There should be a diffuse sound field in those chambers, meaning that there definitely have to be a random subsystem. And this is the case for the full frequency range. In the middle, we have an aluminum panel of size 0.5 meter and 0.8 meter, and that means it is a deterministic thing because it has a 4 millimeter, so it's somehow stiff. It is, in most frequency range, it is a deterministic subsystem. This plane is modeled by using a modal approach, which makes sense because low deterministic system means there are not that many modes, and this is just, I will later explain how this is done within Python currently. We have two kinds of sources. The first source is exciting the random noise field, so in this case room number 1, and the second source is the case where we are exciting the deterministic part, so the plate here in the middle. Okay, as mentioned, everything is expressed in the modal base. That means we will use a modal transformation matrix in our hybrid equations, and this is given by the modal transformation matrix is just summing up all the particular modes in this matrix. Using this matrix and transforming the stiffness matrix of our mechanical system, in this case the plate, means that we would use here we would get this diagonal version, which is the reason why we are using modal condensation, because it simplifies the equation. However, the other matrices, like for example the stiffness, the radiation stiffness matrix, if we using here the modal transformation, we will not have such a diagonal configuration. So here we have to consider all combinations of all mode shapes, and that means we are losing a large kind of performance of this modal formulation. It destroys the diagonal form. Anyhow, there are specific options that only the important modes are used, but this is would be the subject of another lecture. Okay, so far for the modal approach. If we are applying this in our hybrid equation, as told before, the global, let's say, formulation of the equation doesn't change. So they are base independent, if it's a real base, and this is the case for modes. They're just using the similar formulas for the coupling loss factor and or for the transmission coefficient. Again, you see here the simple sketch of our hybrid model. Excitation of power 1 into cavity 1, force exciting our FEM subsystem in the middle, and the SEA as cavity 2 as a receiver cavity. The total modal radiation stiffness is a combination of the two direct field stiffness matrices and the structural stiffness matrix in the diagonal modal form. There will be an additional term which comes from the damping in the connected FE subsystem, so leading to an extra damping in our SEA. And this is that's an example where the mode shape is, the modal form is at least simplifying the radiating part here, but all the rest is keeping this, let's say, fully populated case that comes from the total stiffness matrix. Okay, so we have collected now all, let's say, more or less detailed formulas to perform our hybrid simulation. What is missing is the simplified version of our mode shape. And this is a case which is quite really simple. I create a mass matrix, which is just using the specific mass related to the area of the element. So it would be the full area if it's a fully surrounded place of an inner node. If it's an edge node, it will be half area, it will be a quarter area if it's a corner node or vertex node. And with this mass matrix and adding all these things together, I can create the mode shapes, which are just taken from the analytical solution. So a very simple approach for rectangular flat systems. However, we need the mass matrix for some components to normalize our system here. Okay, and the modal frequency follow out of the modal frequency solutions from the flat plate example. Good. So we have done the modes, we have set up all the equations, and now we go into our hybrid step-by-step modeling, which could be now much easier explained than in the, let's say, clearly only theoretical approach. Step one, that was setting up the system configuration. So we mapped the known modes to our discrete mesh. We had 888 modes until our maximum frequency of 4,700 Hertz roundabout. We set up all the SEA equation according to our shown SEA twin chamber example, but using the hybrid coupling loss factor here in this case. And we calculate all the modal direct field radiation stiffness matrices using the radiation stiffness matrix that we developed in the coupling loss factor chapter, and using the discrete version, which is a simplified Rayleigh integral with solving the singularity when both are the same using the using the piston approximation. So that means in step one, what are we doing? We just setting up the FEM matrix. That means understand the dynamics of this inner field. We are setting up the SEA matrix. That means we are deriving the damping loss factor and all the coupling loss factors, and we the damping loss factor and the modal densities using the equation that are relevant for cavities, or shown here. And we derive all the important direct field radiation stiffness matrices that we need for the radiation of the deterministic system into our neighboring SEA subsystem. So that means we are just collecting up the most important matrices. Good. So then we come to step number two. Step number two means setting up the system matrices in detail. And the most important matrix, as it was stated before, is the total stiffness matrix. So we just take the stiffness matrix of our plate in the middle here, and the deterministic version. We are adding all the direct radiation stiffness matrices to create the total stiffness matrix. From the direct field radiation stiffnesses in both to both subsystems and the total stiffness matrix, we can calculate, using the hybrid coupling loss factor, we can calculate the coupling loss factor, which gives us the energy flow in the SEA world from this direction and into this direction. And from this, we can then set up the total SEA matrix of our two subsystem SEA system. Good. On top, we have this additional damping component, which brings us this extra damping loss factor coming from the hybrid formulation. If we have a look into our hybrid coupling loss factor result, that's the blue line here. We have this spiky motion going through all the resonance of the plate. We have the stiffness control transmission area. But we see that in the high frequency area, we are approaching the orange line, which would be the SEA solution of the same plate. So this is really quite well confirming then once the plate becomes really random, we can use SEA. However, the reason here is also that the mass law is kind of smoothing out the result. But however, here we have resonant transfer that is well described by the SEA subsystem. We see this typical behavior, mid and low frequency, we need something deterministic, at least for the plate. For high frequency, we can use a full SEA approach. Good, so far for step number 2. So let's come to the next step. The next step deals with, it was just showing some results of the, we are still in step number 2, but we are just dealing with the damping coefficient, which is also part of this matrix setting up process. And here we see that the damping that is given to the cavities due to this expression is extremely low. But that makes sense because it is the damping in the plate, which has damping loss of 1% here. That's what we assumed. And then on top of that, it just has to be coupled to the cavity, meaning that the damping must be low. However, it can be considered. And it is both more or less the same in both cavities. The reason for that is that the modal density is somehow similar in both rooms. Okay, now we really come to step number 3. We apply the loads, external loads. And we have two situations. We have this power, 1 watt power source in the room. So this is the power excitation which goes into the SEA subsystem, here denoted by the green symbol, or here the green symbol in our step description. And we have the 10 Newton root mean square point force that is exciting our plate at a specific position. So at x 0.1 and y 0.11. So the point coordinates, these are the coordinates of the plate where it is excited. So then we have defined the sources, and the next step is now to apply them. And first of all, and if you remember well, is we start with the power input into the FEM subsystems. And that means we are just calculating this extremely complicated, let's say, we get the response of our subsystem in relation to our force. And from this, let's say, cross-spectral density displacement response, we can calculate the power input to the connected subsystems. However, we have a fully deterministic load, and in that case, it's much more convenient to solve the deterministic case. That means we solve this equation here with a total stiffness matrix, calculate the response, and then at the end calculate the cross-spectral density out of this to use the power input into the neighboring SEA subsystems. Okay, next step. Let's say the result of this first step is what is the power input into the FEA subsystem from the force excitation, and obviously you see these resonant behavior coming from the plate radiation when there is a modal, when then there is a mode in the plate, smoothing more and more the higher we get with our frequency. And it's the same power input, obviously, because it's only depending on the direct field radiation stiffness, which is the same into both rooms because it's the same plate and the same connection. That's the power input that's given to both cavities or rooms. Okay. Then the next step is then the other system. That we would like to get the root mean square value from this plate, and this is just reconstructed then obviously by modal coordinates, because I mean one response is the let's say the displacement of the plate due to the force excitation, but from extracting this back from the modes we can get the root mean square let's say velocity of the plate, which is, let's say, the SEA-like quantity that we would like to have at the end of our calculation. So, to conclude, the FE subsystem is more or less finalized with respect to the deterministic excitation. Step 4.2. Now we solve the SEA equations with the SEA and the power which comes. So we're using just the directly random power input into our first cavity, plus the power that comes from the FE radiation. And for let's say better understanding, I have separated this in the both graphs here on the left on the right hand side. So so here on the left hand side, this is just the power excitation, the pressure that comes from the excitation in the cavity number 1. I'm not showing cavity number 1, I'm just showing the results in cavity number 2. And you see that is the power that is just linked to the coupling loss factor between both cavities, giving this, let's say, resonant result in the low frequency and kind of smooth result in the high frequency again. And this is linked to the coupling loss factor, fitting very well to the corresponding SEA result, which is given by the orange line. When we check on the right hand side, this is the pressure in the cavities coming from the force excitation. And here we see a very spiky resonant behavior in the low frequency. But even for the force excitation, we have a, let's say, quite a good agreement with both SEA results, but very late. It has to be just above 2 kilohertz. We can use SEA to calculate the radiation from the force excitation, using all the assumptions that you use if you do SEA on the plate. Good. So far for step number 4.2, and now we come to the last step, and this is a sub-step of number 4. And this is calculating the FE response due to the energies in the SEA subsystem. That means now I calculate the back effect of the reverberant fields onto the FE subsystem. And here I'm using the classical diffuse field reciprocity equation again, and which gives me the let's say the cross spectral density of the excitation of the reverberant field, and then I get the response of the plate again. So coming back, so this is, I get the energy from the SEA solution shown in the slide before. Using this energy and using the diffuse field reciprocity, I can calculate the response due to the reverberant field in both cavities. And from this, again, I can calculate the averaged velocity. Good. At the end, step number 5, I have to add both results. So just to separate, I mean, the blue line, that's a response due to the force on the deterministic subsystem. And the green result, the other shape here, this is the response coming from the, which comes from the reverberant excitation. This I have to add at the end of the day in our final step of the hybrid solution. And let's have a look again on the results. We start with the results on the plate, and there we have a really interesting effect. First of all, the simple, let's say, the result from the reverberant excitation in room number 1, that is the blue line. When we then using the resonant SEA result, please keep in mind the resonant SEA result is not representing the mass law. I told you that you have this funny mass law thing. So we have the resonant path and the non-resonant path, which is the mass law. In that case, you would get the orange line. And you see, with the orange line, you will never ever approach the hybrid solution because the forced motion is missing. When we're using the formula that was presented in the plate example, in the SEA session, we have to add the non-resonant motion. And if we do so, we get then finally the corrected SEA result. And doing so, we have an excellent agreement. So showing again, if you apply the non-resonant correction to your SEA results. You can use SEA results, however, you have to do this manually. In Piva it's implemented. In many commercial softwares, you have to do this manually. Good. So on the right-hand side, we have the next thing. We have here the blue line, that the result of the force excitation of the plate, somehow fitting to the SE result in high frequency. But you know, again, that all the assumptions for SEA modeling of plates are quite harsh. So they are not so precise like for the 3D systems. But however, there is a quite a good agreement. But you also see that the additional part that comes from the let's say from the reverberant field on top, so only the reverberant field that is, let's say, coming back from the radiated power and then back exciting our plate, it can be neglected. It is very low here in the for the orange case, for the high frequency area. Okay, so hopefully this has given you quite a good idea about how hybrid systems are modeled and brings, let's say, some more practice into the full hybrid modeling scheme. However, you have learned there are a lot of steps. If you have a full system of hybrid models and if you have excitation on the statistical systems and on the deterministic systems, a hybrid solution might become complicated. Good. However, you have also seen you get a very precise and fast transmission loss result. And this is what is very often used in typical transmission loss calculations, because you don't have to recreate the diffuse sound field, because you have the diffuse sound field already implemented if you know the radiation stiffness with the given diffuse field reciprocity. So I hope you had some fun. It was not too complicated and helped to understand hybrid methods. And the next session will be number 25. And this will be the last session dealing with a lot of industrial cases that shows SEA and hybrid methods in the real industrial applications. See you later and bye-bye.